begin. Last time, our topic was CBS, that is Cantor-Bernstein-Schroeder theorem, CBS theorem, which states that if A is embeddable into B, that is, there is an injection, there exists an injection, from A to B. If A is embeddable to B, and likewise, if B is embeddable into A, then these two sets are equivalent to each other. That is, there is a bijection. While neither of these two injections must be a bijection, yet nevertheless, there should exist a bijection between A and B. Whenever you have two bijections in both directions. So then we applied this result to prove some interesting facts. First of all, we have proved that n is embeddable, naturals are embeddable into integers, which is, of course, obvious. Integers are embeddable into rationals, and rationals, which is a little bit less trivial, are embeddable into the set of all triplets of naturals, which is, of course, equivalent to n. So, naturals are embeddable to interrationals, and rationals are embeddable into naturals. That is, all three sets are pairwise equivalent according to our Cantor-Schroeder-Bernstein theorem. So, and another application of this theorem we saw last time is as follows. We considered the set of all real numbers, and we took as a known fact that the set of all real numbers is equivalent to the set of all sequences of zeros and ones indexed by natural numbers. So the set of all binary valued functions from naturals. So we have taken this fact, and also we know that this set is equivalent to the set of all subsets of naturals. And then, using this fact, we have proved the following. So reals are, of course, equivalent to the set of all pairs, where the first coordinate is some arbitrary real, and the second coordinate is fixed to be 0, while this set is, of course, embeddable into the set of all pairs of reals, as it is a subset 0, and this set is equivalent to this one, according to our quoted earlier fact. So while this one, 2 to the power n multiplied by 2 to the power n is, of course, equivalent to this set according to our theorem. So, and of course, we know that 2 times 2 is 4. This set of pairs of zeros and ones, there are exactly 4 such pairs. This set is equivalent to the set of the first 4 naturals. So we have that this set is equivalent to the set of all functions from naturals to 0, 1, 2, and 3, which is a subset of the set of all natural valued functions from naturals, which is a subset of the set of all real valued functions, which is by definition equivalent to this set, once we may obtain this one, and then using the fact that the square of naturals is equivalent to the set of naturals itself, then we may obtain reals. So that means that all sets mentioned here are pairwise equivalent according to our CSB theorem, because every one of these sets is embeddable into R and vice versa. So, for example, as a corollary, we may obtain that the set of all reals is equivalent to the set of all real pairs. Or, in other words, the line is equivalent to the plane, which is a little bit counterintuitive. And of course, each of these two sets is equivalent to the set of all functions from naturals to naturals, or all functions from naturals to reals. So this one is a set of all functions from naturals to reals, and these functions are sequences which you are familiar with from your calculus course. So these are just sequences of reals. Is it clear? Is it clear? Any questions? So please. This was a little recap of our previous lecture. Dear students, does anyone have anything to say or to ask? So please, be more active. So no questions so far. But anyway, I will continue. So, up to this point, we know something about comparing sets by their cardinality, their number of elements, informally speaking, in general. So, one of the most useful facts is our CSB theorem. Also, we know, say that the set of all functions with two values from A to 2 is equivalent to the set of all subsets. Or, for example, we know that for any natural number n, the set of all ordered n tuples of all n tuples from the elements of A is equivalent to the set of all functions with finite domain. So we know some facts like that. But now our next move is to explore finite sets and their cardinalities. So we want to formally introduce the notion of number of elements for the finite case, of course, because we don't know what an infinite number could be. So just for finite numbers. Let me recall that we have already considered sets like n underlined, which are formally defined as sets of first n naturals. So this is the set of all naturals strictly less than n. It is a subset of the set of all naturals. Clearly say 2 underlined is just 0 and 1, and say 5 underlined is 0, 1, 2, 3, 4. First 5 naturals. And what is 0 underlined? So please, what's 0 underlined? The set of all naturals which are strictly less than
Empty.
the empty set. Of course, we have no such natural, and if we take all them together, we will obtain nothing. The empty set. Okay. By the way, the set of all naturals which are strictly less than n plus 1. So please switch off your microphone. If you don't, thank you. Okay. So this is the set of all naturals which are less than n and n itself. That means that x is less than n plus 1 if and only if, of course, x is either less than n or x equals n. So just that. So, and we will use this set as some examples, some exemplary finite sets. So we shall define a set to be finite using this n underlined. So the definition: A is finite. It is finite by definition if and only if there exists some n, which is a natural number, so that A is equivalent to n underlined. So a set is finite by definition if and only if it is equivalent to some n underlined. A is infinite. It is infinite by definition if and only if A is not finite. That's quite trivial, but this definition of infiniteness, of infinity, is not very good in practice. So we will have to improve it a little. Okay, a finite set is by definition any set which is equivalent to some n underlined. But here we have a little question. For a given finite set, is this number n unique? Should it be unique? Or is it possible that we have, say, 2 or more distinct n which are equivalent to A? Is it possible? Is it possible that, say, A is equivalent to n and also to m, where n and m are distinct? Is it possible or not? Of course, this question boils down to the following. Is it possible that n is not equal to m, yet n underlined is equivalent to m underlined? So, what about the number of elements in this set? Intuitively, we know that this number is n, and these sets are distinct, that is not equivalent. They are not equivalent for distinct n. But how is it possible to prove it? Of course, we may say consider this set, this one, and prove that they are not equivalent. How is it possible to do that? You may consider all possible functions from this one to this one, and for each function, you may prove that this function is not a bijection. So let's take some function from 2 to 3. So please give me one. Let's define it by the equations. So f of 0 equals what? Let's consider some example. So please.
1,
1. And for 1?
2,
Say 2. Why this function is not a bijection? Why?
it's not surjective.
Of course, it's not surjective. Not surjective. It doesn't take value 0. So it's not a bijection, but of course, we have 9 functions from 2 to 3. As there are finitely many of them, we may of course consider all and prove that no such function is a bijection. And in fact, no such function can be a surjection. But what can we have in general? How is it possible to prove that these two sets cannot be equivalent when n and m are distinct? How is it possible to prove it in general? Prove it to mathematical standards of rigor. Of course, that's possible, but we shall need induction. Let's prove the following lemma. For each natural number n, if f is some function from n plus 1 underlined, I will omit this word underlined in my oral speech. So if f is a function from n plus 1 to n, then f is not injective. Of course, there is a dual fact which states that if f is a function from n to n plus 1, then it cannot be surjective. As in our case, of course, it's not possible to surjectively map 2 to 3, because on 2 elements, it's not possible to have 3 distinct values. But anyway, let's return to our formal rigorous presentation. So if f is a function from n plus 1 to n, then it is not injective. How is it possible to prove it? Let's try. Assume the contrary. What does it mean, the contrary? That means that there exists some n, which is there exists some n and there exists some f. Of course, there is a quantifier on f, such that f is an injection from n plus 1 to n. But now we will apply the least number principle. By the least number principle, we can take the least. We can take the least such natural number n that there exists some injection from n plus 1 to n. So let's take the least bad number. Let's take the least bad number. And now our usual case analysis. The first case is when n is 0. So then we have that our f is an injection from 0 plus 1, that is 1, to 0. So we have a function from this set, 1 underlined, to the empty set. Is it possible to have such a function? Does there exist a function from something to nothing? A function must be total.
No.
No, that's not possible. That's not possible for from this one, as f is total, it follows that f of 0 belongs to the empty set, but the empty set has no element, so that's not possible. So our first case leads us to a contradiction. It's not possible to have such function. We have assumed the contrary and have got a contradiction. So this case is done. The second case is when our n is greater than 0. But we know that if a natural number is greater than 0, it is of the form m plus 1. So our n is m plus 1. And of course, then n plus 1 is m plus 2. So we have some injection from m plus 2, that is n plus 1, to n, that is m plus 1. This set has the greatest element. Which one? Which element is the greatest in this set?
n plus 1.
Of course. And here?
M.
And here the greatest element is m. So I have something like that. 0, m plus 1. And here all elements from 0 to just m. And we have an injection. Our goal is as follows. We know that n is the least bad number. The least number for which this pathological, this strange injection is possible. So we have to show that if this is possible for n, it is possible to construct such an injection for some less number. And now let's see what f does. Assume that our f, assume for a moment that our function f maps m plus 1 to m. But then what it does with all numbers which are less than m plus 1? It maps them where to? If it is an injection.
From 0 to n.
From 0 to m. So here we have something like that. These numbers from 0 to m, they comprise the set m plus 1 underlined. Do you agree? all numbers less than m plus 1. From 0 to m, inclusively. M plus 1 underlined. And here we have all numbers from 0 to m exclusively. So all numbers less than m. So we see that our function f being injective, as it is an injection, it can't take this value m twice. It can't take this value twice. So it must map all numbers from less than m plus 1 to all numbers from m underlined to the set of all numbers which are less than m. And it does it injectively. So that means that our function, if we restrict it to all numbers less than m plus 1, it is an injection of m plus 1 to m, while m plus 1, so let's consider, say, some function, let's call it somehow g. What's g? G is a function from m plus 1 to m, and it is the same as f, but on a restricted domain. So this function g is an injection from m plus 1 to m. But we know that m is strictly less than n. M is less than n. So we have an injection we have a strange injection for a lesser number. N was chosen as the least number for which this situation is possible. But we see that it should be possible for some even lesser number. So we have got a contradiction. Is it clear? Is it clear? Or do you have any questions?
Can you repeat why is contradiction?
A contradiction is as follows. Do you agree that G is an injection from m plus 1 to m?
Okay.
So this, what's G? G is the same as f, a part of f. It is an injection, but we have assumed that n is the least number for which there exists an injection from n plus 1 to n. N is the least bad number. M is, of course, less than n from here. But we have constructed an injection from m plus 1 to m. That's a contradiction. Is it clear? The contradiction is with the choice of n. N was the least number for which an injection from n plus 1 to n is possible, from the next number to this one. And we see that for some lesser number m, that's also possible. Is it clear or not? That's quite important. So please give me some feedback. Dear students, is it clear or not?
Yes.
Yes.
So, but this all this argument leading us to the contradiction is all this argument depends on some assumption, namely that our f maps m plus 1 to m, that is the greatest element on the left to the greatest element on the right. But in general, it is not true. In general, of course, it is well possible that f maps our m plus 1 to some other element, not necessarily this m. But what can we do then? We can just replace this x, the image of m plus 1 with m and vice versa. So let's do this more formally. Okay. So 0, m plus 1. So this is our n plus 1 underlined. You know, n plus 1 is just m plus 2. This is n underlined. Here we have one less element. And we have some function f. And this function maps m plus 1 to whatever x. Okay. And now let's consider the following function h. Let's consider the function h, which is from n underlined to n underlined. By the way, n is m plus 1. n plus 1 is m plus 2. And this function h just changes. It just swaps x with m, nothing else. And formally it acts as follows. H of k is m if k equals x. It is x if k equals m, so it swaps these two values. And otherwise, when k is neither x nor m, it doesn't change its argument. Is it clear? A simple function that swaps two values. Is this definition clear?
Yeah. Why k equal m when k equal is?
It is not necessary. If, that means if k equals x, then it returns m. If k equals m, it returns x. So this is the definition of our h. I want to define h this way. May I?
Yes.
So I want to consider such a function. It clearly exists. So the following question: what can you say about H? Is it, say, bijection? Maybe is it a bijection or injection at least?
Bias.
Of course, that's a bijection. Clearly, our H is a bijection of our right hand side set. It is a bijection, and of course it is an injection. We need just that. H is an injection. Okay. And now let's consider the following function. Okay, let's consider G. What's G? G is a function from this set. It is just the restriction of f onto this first m plus 1 number. So G is from m plus 1 to n, to this right hand side set. So what's G? G is defined the following way. It is the same as f. G of x equals f of x. But G is not defined at m plus 1. G is defined only on these first numbers. But its values are the same as for f. Is it clear?
Yes.
So, and now let's consider one more function, g prime. That's not a derivative, by the way. G prime is by definition the composition of our G and our H. Interesting. What can we say about it? By the way, is G injective? I have a serious question for you. Is G injective?
Yes.
Of course, because as f cannot, that's obvious, but let me demonstrate it. What if g of x equals g of y? Then, of course, from this equation, f of x equals f of y. And then, as f is injective, x equals y. So G is injective. G is injective, H is injective. But what can you say about the composition of two injections? It is injective. The composition of two injective relations is injective. We know that. It is injective. Is it clear?
Yes.
Okay. And now, what can we say about the domain of G prime? G is a function from m plus 1 to n. Okay. H is a function from n to n. That means that this is a function from m plus 1 to n. By the way, n is just m plus 1. So G prime is an injection from m plus 1 to m plus 1. So, for now, we have such an injection. But this injection is special. This injection is special. It cannot take the value m. Why is it so? Oh, I have the following proposition. I say that m is not a value of G prime. So it cannot take this value. Let's prove it. That's quite easy to do so. Assume that m is an element of the range of G prime. What does it mean? Then there exists some k from m plus 1, so that G prime of k equals m. Do you agree? This is by definition.
Yes.
But what is G prime? It's a composition. So h of G of k equals m. Ha! So that means that h of G of k equals m. Is it clear?
Yes.
But when h equals m, let's return to the definition of h. At which point?
S.
Just x. X and only x. But x, by the way, is the f value of m plus 1. So we see that G of k equals x. And what's x? X has been chosen as the value of f at m plus 1. It is f of m plus 1. And this is G. You know, G is the same as f, but restricted to a less set. So that means that f of k is the same x. But what is the domain of G? Here it is. The domain of G is the set of all numbers from 0 to m. All numbers less than m plus 1. Is it clear?
Yes.
So that means that our k is less than m plus 1. Ha! If it is less than m plus 1, it doesn't equal m plus 1. Yet, nevertheless, f of k equals x equals f of m plus 1. This is a clear contradiction, as f is injective. F is injective, so it's not possible that f takes the same value at two distinct points. Is it clear?
Yes.
I didn't understand the first 3 lines of the proof.
These 3 lines.
Yes.
Okay. Let's repeat. I have assumed that m is a value of G prime. What does it mean that it is a value? It belongs to the range. That means that at some point of the set m plus 1, our G prime takes the value X. Is it clear?
Yes.
But what is G prime? G prime is a composition of G and H. What is the value of the composition? It is H of G of K. So this value equals this one, because G prime is just such a composition. Is it clear?
Yes.
So, and of course it should be equal to M, as this one equals M. I see that H of G of K equals M. Then I recourse to the definition of H. When H takes the value M at the only point X. Is it clear?
Yes, I understand.
Okay. And then I'll exploit the fact that our G is defined on M plus 1 underlined. So either F is not injective, or it's not possible for G to take a value X. Take the value X. Is it clear?
Yes.
So let's see let's see our sketch. G is the same as F, but restricted to this domain, to this set. As G is and F are injective, it's not possible that G takes the value X, as F take it at some point without our domain. So it should be clear.
Excuse me. I have a question. For this sketch, F always is M plus 1?
What's M plus 1?
A point?
M plus 1? So we have points M and M plus 1 in this set. Is it clear?
Yes.
F is a function from N plus 1 to N, underlined. So F is a function. It takes some value at this point, M plus 1.
Yeah.
I want to denote this value by X. X is by definition just the value of F at M plus 1.
Yes. So X is always the last number.
No. That's my point exactly. Even if it is not M, even if it is not the greatest number, I may swap it with the greatest number using some H.
No, I mean the range in the left.
X
Is always the last.
X is the value at the last point. The value at the greatest point of this set. Yes, that's it. M plus 1 is the greatest number in the set N plus 1 underlined, and X is the value of F. Is it clear?
Yes.
Okay. So, for now, I know that M is not in the range of G prime. And G prime is an injection from M plus 1 to M plus 1. It is an injection from m plus 1 to m plus 1, but it doesn't take m as a value. It doesn't take m. So that means that all its values belong to m plus 1 minus m. So G is an injection from m plus 1 to m underlined, to all to the set of all points of m plus 1 underlined except m. Is it clear?
Yes.
But it is still an injection. Ha! I have constructed an injection, a bad injection, that is from greater set to a lesser set, from m plus 1 to m. I have constructed a bad injection for some number which is strictly less than n. But previously, I have taken n as the least number for which this is possible. So I have taken n as the least number for which such an injection is possible. And nevertheless, I've managed to construct such an injection for some lesser number. This gives me a contradiction. It is a contradiction with the choice of n. N was the least such number for which an injection from that number plus 1 to that number is possible. So that's a contradiction. The same way as we previously saw, but now in a little bit more general situation, when the value of f is not at m plus 1, not necessarily m, but it might be some other number x. Is it clear?
Yes.
So, let's review our proof. I want to prove that for no natural number n, for no function, it is possible that this function is a function from n plus 1 to n, and it is injective. So if it is a function from n plus 1 to n, it is not injective. How is it possible to prove this statement? Assume that this statement is not true, that is, there exists some n for which there exists some function f from n plus 1 to n, which is injective. So the implication is not true. That is, the conclusion is false. So f is injective, but the assumption is true. Assume that it's not the case. By the least number principle, I can take the least number n for which there exists an injective function from n plus 1 to n. It is clear that this n is not 0. As it is not 0, it is some m plus 1. Assuming that n is m plus 1, I can cleverly construct a function g prime, which will be an injection from m plus 1 to m when m is less than n, which is not possible, as n has been chosen as the least such number. Is it clear?
Yes.
And now let's harvest some corollaries from this lemma. First of all, they are very easy. So we have done the most of the technical work here. So theorem, which is widely known as the pigeonhole principle. The pigeonhole principle. Or in Russian tradition, it's usually called Dirichlet's principle. For the prominent French mathematician Dirichlet, Dirichlet's principle. But in the English-speaking world, it's widely known as the pigeonhole principle. So this principle says as follows. If m is greater than n, then it is not possible to embed m underlined to n underlined. So there is no injection from m underlined to n underlined when m is greater than n. So, for example, it is not possible to inject 5 elements, to embed 5 elements into 3 elements. It is not possible for however great numbers. So this number is not embeddable into this one. So that's not possible, and so on. Is it clear? If m is greater than n, then there is no injection from n underlined from m underlined to n underlined. So you may informally you may state it the following way: if m is greater than n, it's not possible to place m distinct objects to n distinct boxes, so that each box contains at most one object. So you cannot put m rabbits into n cages, so that there is no more than one rabbit at each cage. When you have more rabbits, then you have cages. And formally, that means that there is no injection. Is this statement clear? Is it clear?
Yeah.
And now I want to prove it. Assume the contrary. That's very easy. Assume that there exists such an injection. Assume that F is an injection from M underlined to N underlined. Okay. I see that. So F is an injection from M underlined to N underlined. I know that M is greater than N. So what does it mean? That means that M is at least as great as N plus 1. It is equal or greater than N plus 1. Do you agree?
Yes.
That means that N plus 1 underlined is a subset of M underlined. So that means if it is a subset, we have already observed it. If it is a subset, it is embeddable. Do you agree?
Yes.
So I obtain the following situation. N plus 1 is embeddable into M. M is embeddable into N. So that means by transitivity that N plus 1 is embeddable into N, which is not possible by our lemma. That's all. Is it clear?
Yes.
So there is no injection from M underlined to N underlined when M is greater than N. Corollary. If N is distinct from M, then these two underlined sets are not equivalent. So for distinct numbers, our N and M underlined are not equivalent. That's also very easy to understand. If N is not equal to M, then either N is greater than M or M is greater than N. Do you agree?
Yes.
So by the pigeonhole principle, by the pigeonhole principle, that means that either N is not embeddable into M, or M is not embeddable into N. But in either case, these two sets are not equivalent. You know, two sets are equivalent if and only if they are mutually embeddable. And if we have no injection from N to M or from M to N, then they are not equivalent. Is it clear?
Yes, yes.
So that's quite clear. Now, what does it mean? If you remember, maybe you remember that we have defined a set to be finite if and only if it is equivalent to some N underlined. So our last statement means that this N is unique. This N is unique. It is not possible to have two such distinct numbers. So we may state it the following way as another very important corollary. Another corollary. For every finite A, there exists a unique. Do you know this symbol? There exists a unique.
Yes.
There exists a unique. There exists a unique such natural number n, such that A is equivalent to N underlined. So this number is unique. This number is uniquely connected to our A. And this number has a special name with respect to the set A. N is called the cardinality of the set A, or also it's called the size, the number of elements So dear students, we've made some progress of some importance here. We have formally defined what the number of elements is. for finite sets, at least. So the number of elements of a finite set, or the cardinality, or the size thereof, is just that unique n for which our set A is equivalent to n underlined. We have obtained a formal definition of our intuitive notion of the number of elements. It's quite important. And in this case, we shall write this way: the cardinality, or the size of A, equals n. Clearly, two finite sets, if they are finite, of course, two finite sets are equivalent if and only if their sizes are equal. Is it clear? Is this clear?
Yes.
So, another interesting point. Why, for example, the set of all naturals is infinite? Let's prove it formally. In order to prove it formally, we must use our definition of infiniteness. A is infinite if and only if it is not finite. So it's not possible to take some natural n for which our set is equivalent to n underlined. So assume the contrary. Assume that there exists some natural number, let's call it m, so that the set of all naturals is equivalent to m underlined. And what does it mean? That means that our n is, of course, embeddable, if it is equivalent, into m underlined. But on the other hand, m plus 1 is still a subset of the set of all naturals, whence m plus 1 is embeddable into n. We know that this implies that m plus 1 is embeddable into m, which is a contradiction with the pigeonhole principle. So we have just formally proved that the set of all naturals is infinite. Is it clear?
Yes.
The pigeonhole principle says that it is not possible to embed a greater set into lesser set. And we have a dual result, which is easily reducible to the pigeonhole principle itself. It is not possible to construct a surjection from a lesser set to a greater one. Let's state and prove it. Another theorem. So it is the dual to the pigeonhole principle. If m is greater than n, and f is a function from the lesser set to the greater one, then f is not surjective. So if you have just n rabbits, you cannot put them to m cages where m is greater than n in such a manner that every cage contains at least one rabbit. So there is no surjection from a lesser set to a greater one. So the proof is very easy. Assume the contrary. Assuming the contrary, we have that m is greater than n and there exists some surjection from n to m. Let's make a drawing. So n is less than m, yet nevertheless we somehow have constructed a surjection. Okay. And now let's define the following function g, which would be from m to n, and this function is defined the following way. G of k is the list x from n underlined such that f of x equals k. So this is the least preimage. What does it mean? Say we have k. So G maps this k to its least preimage. Is it clear?
Yes.
Of course, G is well defined. Why? Because G is total. G is total as F is surjective. As F is surjective, that means that for every x, for every k from M underlined, there is such x. And by the least number principle, we can take the least one. So G is total as F is surjective. And my point is that G is an injection. So G is a function. It's indeed a function from M to N. I say that G is injective. That's easy. Indeed. Assume that G of k equals G of L. Assume that we have two values to be the same. But what is G? G of k is the least x such that f of x equals k. That means that f of G of k equals what? Dear students, please tell me.
F of k.
No! Think a little bit more. G of k is some number for which f of x equals k. You know, G of k equals this x. So f of G of k equals what?
K.
Of course. That means that f of G of k always equals k. Ha! So then f of G of k from on one hand that equals f of G of L, And on the other hand, this equals k. And this right-hand side also equals L. So k equals L. That means that it is indeed injective. What does it mean? That means that G is an injection from M to N. While we know M is greater than N. M was greater than N. So that's not possible by the pigeonhole principle. It's not possible to construct an injection from a greater set to a lesser set. So by the pigeonhole principle, we can obtain a contradiction. That's not possible. So what is the main idea here? If there is such a surjection, we may construct the so-called right or the so-called right inverse to it. Namely, you can take some function g, which maps every element from M to its least preimage, to the least point where this value is taken. This function is injective, so this is an impossible injection. So you will obtain a contradiction. So we know now that it's not possible to have a surjection from a lesser set to a greater one. And the last result of this kind,
Excuse me.
Uh-huh.
I have a question for f of g of k is equal to k. G of k is equal to x or is equal to k?
G of k equals the least x such that f of x equals k. Just read these words. G of k equals x. And f of x equals k.
Okay, thank you.
So, or you may look at this sketch. So G maps k to some x, which is mapped to k by f. So we have something like that. Here we have k. So that's f. It is not necessarily injective. And what is G? G just takes the least x from this preimage. Is it clear?
Yes.
So there is no surjection from a lesser set to a greater one. And the last result of this kind, which is also very useful for discrete mathematics, or I dare say for computer science even, but I won't prove it, for it is it would require some a little more technicalities. Maybe it would be beneficial to prove it at your seminar. So let A and B be finite. Let A and B be finite. And equivalent to each other. So we have two finite sets of the same cardinality. Then for every function from A to B, f is injective if and only if f is surjective. So what does it mean? That means that if you have two finite sets with the same number of elements of the same size, then every injection is a surjection and vice versa. So we may consider, say, the following practical example. Assume that we have 10 students and 10 marks from 1 to 10. If we assume that no two distinct students have the same mark, so if all the marks are distinct, then all the marks were used. So if 10 students have 10 marks, so that this is an injection, no two distinct students have the same mark, that means that all marks are used. So every function between two finite sets of the same size is injective if and only if it is surjective. And the very important point, this is not true for infinite sets. That's not true for infinite sets. Why is it so? Let's consider the function f from naturals to naturals, so that f of x equals x plus 1. Is it injective?
Yes.
Of course, this function is injective. That's obvious. It maps 0 to 1, 1 to 2, 2 to 3, and so on. And of course, it is injective. Is it surjective? Which value it doesn't take?
0.
Of course, that's not surjective. And this idea might be used as the base for an alternative definition of an infinite set. You may define an infinite set as a set for which there exists an injection from the set to itself, which is not surjective. And in view of so-called axiom of choice, this definition would be equivalent to ours. So this observation might be the base for an alternative definition of finite and infinite set. But anyway, let's memorize this very useful fact. If two sets are finite and of the same size, then every injection between them is a surjection and vice versa. This is very useful in combinatorics and the like. So, any questions, please? Thank you, dear students. This was our last lecture in the first part of our course, which is known as mathematical thinking. Probably we shall seamlessly continue. So continue just this line of Pigeonhole Principle and finite cardinalities and so on in our new semester, but under the different name of the basics of mathematical logic. Of course, we will add some logic to this broth. Okay, we shall have a simple written test, And this test with your homework results, this all this will be used to give you your final grade for the first semester. So,
Thank you very much.
thank you, dear students. If you have any questions, so please don't hesitate to post them to our group. I'll try answer them as soon as possible. Thank you, dear students.
Can I give one question?
So
if
please,
possible, ma'am?
of course.
Let's take one function, and is it possible that if f is not functional, that f is injective?
Aha. It is not a function if it is not functional. Assume that we want to construct a relation, a binary relation, which is not functional but injective.
Injective.
R is injective. It is injective, but not functional. Of course, that's possible. And it's very, very easy to construct one. Okay, let A be so injective and not functional. Okay, let A be a set of 1 point, say 0. B is a set of 2 points, 1 and 2. I want to make it not functional. If I'll have these two pairs, so let's I be just the set of two pairs, 0, 1 and 0, 2. Is it functional? Obviously, it is not functional. Is it clear?
Yes.
Is it injective? It is injective. For here we have no breakage of injectivity. Injectivity means that for each x, y, and z, whenever x are z and y are z, then x equals y. And here we have just 1 point in the left-hand side, just 1 point in the domain. So every x equals y. So both x and y are necessarily equal to 0. So they are the same. It is injective and not functional. Is it clear?
Yes, it's clear. Thank you.